You probably think of it as, well, a void, right? Just emptiness. But what if that empty space is actually uh, buzzing with activity?
It's a fascinating thought.
And what if it holds secrets? Maybe even the key to understanding huge things like gravity or, I don't know, reality itself.
It's a question that's really driven science for ages, hasn't it? And it's still pushing physics today.
So today, we're doing one of our deep dives. We're going to explore this long quest humanity's been on to understand the fabric of reality.
We'll be looking back at older ideas like the ether,
Right, that idea of a medium filling space.
and then jumping right into modern physics, looking at the quantum vacuum. It's this picture of a hidden, super energetic universe.
Yeah, our mission here is really to unpack all of this, the surprising links, the debates, the mysteries, and give you a kind of shortcut to getting informed about what might be underpinning our physical laws.
We'll touch on history, some pretty cutting-edge theories, and the actual experiments that are testing these ideas.
Okay, let's get into it. So this idea of something filling space, it's not new, is it?
Not at all. For a long time, classical physics had this concept of the luminiferous ether.
Luminiferous ether, right? The light-carrying stuff.
Exactly. An invisible substance they thought light waves needed to travel through, kind of like sound needs air. It was a mechanical explanation. Made sense at the time.
Gave a picture you could grasp.
It did. But it ran into trouble. Famous experiments like Michelson-Morley,
Ah, yeah, they tried to measure Earth moving through it.
they did, and they couldn't detect it. That, plus Einstein's theory of relativity. Well, relativity showed light didn't need a medium. Its speed was constant.
So mainstream physics mostly just dropped the ether idea.
Pretty much, yeah.
Yeah.
It seemed unnecessary.
What if dropping it was maybe a bit premature? I've come across this really interesting, though, admittedly speculative modern framework. It's called the Aether Physics Model, or APM, and it's trying to bring the ether back, but in a completely different way, like a quantized ether, trying to link quantum mechanics and general relativity. What's the core concept there?
Well, the big difference from the old idea is that this proposed ether isn't static. It's not just sitting there.
Okay.
APM suggests it's a dynamic, locally moving medium, kind of an active background for reality.
Dynamic. How does that work?
The proponents argue this dynamic nature actually fits with those old experiments, like Michelson-Morley, that seem to disprove the static ether. It's a different beast altogether.
So a total rethink, not just digging up the old concept. How does this dynamic ether change something basic, like how we think about light?
This is a major shift from the standard view. APM argues light in a vacuum isn't a transverse wave,
Right.
wiggling side to side.
Right.
Instead, they propose it's a longitudinal wave, a compression wave moving through this ether.
Like sound waves, pushing and pulling.
Kind of like that, yeah. The key goal here is to get back to a mechanical explanation for things like polarization, which usually needs that sideways wiggle. It's driven by this idea that if we truly understand something, we should be able to visualize it mechanically.
That's a really bold move, rethinking light itself. And what about quantum effects? Those often seem so abstract, almost magical. Does APM try to give them a mechanical picture too?
It does. Take the photoelectric effect, usually explained with photons, right? Little packets of light.
Mm-hmm.
APM reinterprets that. It suggests photons are more like packets made up of many wave oscillations in the ether. The aim is always to ground these quantum things in, real mechanical motions, make them less abstract.
So less reliance on just the math describing effects and more focus on a potential underlying mechanism.
Exactly. They emphasize using language very strictly, avoiding what they see as treating abstract math concepts like fields as if they're physical things without a clear mechanical basis.
Interesting. This desire for visualization keeps coming up. Now, APM also talks about a singularity. That sounds like the Big Bang, but I gather it's different.
Very different, yeah. In APM, the singularity isn't a one-time event. It's described as this dimensionless point of infinite potential, an ongoing process that exists sort of outside our space and time.
Ongoing, so it's continuously creating things.
That's the idea. Continuously giving birth to matter, energy, fundamental forces, and from it, they say, four primary things emerge. Dark matter, something called G-force, electrostatic charge, and magnetic charge.
Okay, G-force, that sounds important. Is that meant to be the unifying element?
It seems to be positioned that way, yeah. G-force is proposed as this universal reciprocal force that permeates all of space.
And other forces come from it.
Right. The idea is that all the fundamental forces we know, gravity, electrostatic, even the strong nuclear force, they all emerge from how this G-force interacts with the Aether units.
Wait, even the strong force?
They actually reinterpret the strong nuclear force as being fundamentally a magnetic force within this framework. And G-force on the cosmic scale is also suggested as a possible driver for dark energy. It's very ambitious.
Hugely ambitious. So what about the structure of space itself? Or particles? What do they look like in this model?
Well, it suggests space is made of discrete, quantized ether units with specific geometries. And subatomic particles, like electrons, are proposed to have a fundamental toroidal shape, like a donut.
A donut structure, okay.
They also introduce chronovibration, the idea that time isn't smooth but results from oscillations, almost like a flicker. It's all about trying to build a concrete, visualizable structure for everything, right down to the base level.
And dark matter, we still don't know what that is. Does APM have a specific candidate?
It does. It proposes dark matter isn't some new exotic particle, but actually one-dimensional circular strings of mass.
Strings, like string theory.
Sort of, but emerging from their singularity concept. These strings then get trapped within ether units, and that combination forms the visible matter we see. It also brings in magnetic charge as fundamental, distinct from electric charge, which they use to offer new takes on things like the quantum Hall effect.
Wow. Okay, this model is definitely trying to offer a complete picture, but you said it's speculative. What are the big hurdles for APM?
Well, a major one is that its concepts are pretty novel and quite hard to connect directly to things we can easily measure right now.
Testability is key. Right.
Absolutely. It requires a really big shift in how we think about fundamental physics. And maybe most critically, the mathematical side is still, as they put it, at its infancy compared to the incredibly well-developed and tested math of standard physics.
So it's a compelling vision for some, but the rigorous math and clear experimental proof aren't quite there yet. Does it make any specific predictions that could be tested maybe in the future?
Yes, they do propose some potential tests. Things like looking for tiny deviations in the Casimir effect at very close distances.
Okay.
Or specific, distinct measurements in the quantum Hall effect that might point to these fundamental magnetic charges. Also, high-precision atomic clock experiments, they predict these, might show space itself compressing rather than time dilating as in relativity, and maybe specific patterns in how dark matter is distributed.
Interesting. So there are potential avenues for verification, even if challenging. Now, that's one direction bringing back the ether. But mainstream physics, having set the classical ether aside, what does it say about empty space now?
Ah, that's where we get to the quantum vacuum. And the modern view is that space is anything but empty.
Right. You mentioned it's roiling with vibrating quantum fields, vacuum energy. What does that actually look like?
It means space is filled with quantum fluctuations. Think of them as random, fleeting changes in the energy at any single point.
Random changes. Where do they come from?
They don't really come from anywhere external. They're inherent to the quantum fields themselves. Spontaneous, unpredictable, always happening.
Oh.
Always. It means that even a particle supposedly at rest in a perfect vacuum would still be experiencing this constant microscopic jitter.
Huh. That sounds a bit like something Max Planck talked about way back, didn't he? This zero-point energy idea? I remember it being controversial.
You're spot on. It's directly related. Planck's early, and yes, initially controversial, idea that even a quantum oscillator at its lowest energy state still has some minimum energy. Well, that's now understood as arising from these vacuum fluctuations.
So it's baked into quantum field theory now.
Absolutely. It's fundamental. The ground state isn't zero energy. It's this zero-point energy driven by the vacuum's activity.
Okay, so this isn't just theory then. We have actual proof these fluctuations are real. What's the evidence?
Oh, yes. Solid experimental evidence. Probably the most direct is the Casimir effect.
Right, you mentioned that regarding APM tests too. How does it work in the standard view?
If you take two uncharged metal plates and put them incredibly close together in a vacuum, they attract each other.
Just like that.
Because the space between the plates restricts which wavelengths of these quantum fluctuations can exist there. There are fewer fluctuations inside than outside. So the greater pressure from the fluctuations outside pushes the plates together.
Wow. The vacuum itself exerts a force. That's mind-bending. What else points to this quantum jitter?
There's the Lamb shift. It's a tiny, tiny energy difference between two specific levels in the hydrogen atom.
Unexpected, you mean?
Exactly. Earlier equations didn't predict it, but is perfectly explained by the electron interacting with the vacuum fluctuations of the electromagnetic field. This was a huge win for quantum field theory, especially for a technique called renormalization.
Renormalization, that's the thing where physicists deal with infinities in their calculations, right? Sounds a bit like sweeping things under the rug.
Huh. It can sound like that, but it's actually a mathematically rigorous way to handle infinities that pop up naturally in these theories. Think of it like this. If you try to measure the bare charge of an electron very closely, the value seems to blow up to infinity because of all the virtual particles popping in and out around it.
Okay.
Renormalization is a way to define what we mean by the electron's charge at a certain scale, the scale we can actually measure, effectively subtracting off the infinite part in a consistent way. And it works incredibly well. It lets us make predictions with stunning accuracy.
Like the anomalous electron G factor. I've heard about that.
Precisely. The electron has a magnetic moment due to its spin. Theory initially predicted a certain value, but experiments show it's slightly different.
And that difference
Is explained perfectly by the electron constantly interacting with these vacuum fluctuations. And the agreement between theory and experiment here is astonishingly precise, better than 1 part in a trillion.
1 part in a trillion. That's just incredible accuracy. Okay, what about things like spontaneous emission? When an excited atom just gives off light.
That's another key piece of evidence. Why does an excited atom emit a photon seemingly on its own? It's not random. It's actually forced emission triggered by the vacuum fluctuations of the electromagnetic field itself.
So the vacuum kind of tickles the atom into releasing energy.
In a manner of speaking, yes. It implies the electromagnetic field has to be quantized everywhere, even in empty space, constantly fluctuating.
This changes how you think about fundamental particles, doesn't it? They can't just be simple points if they're constantly interacting with this vacuum foam.
They really aren't simple points in this picture. You get effects like vacuum polarization. The bare charge or mass of a particle gets effectively shielded or dressed by a cloud of virtual antiparticle pairs that constantly pop in and out of existence due to the fluctuations.
So the charge we measure isn't the true charge.
It's the effective charge at our measurement scale. And this screening effect means the strength of fundamental forces actually changes depending on the energy scale you're probing at. As you get closer or use higher energy, you penetrate that screening cloud. This is called running coupling constants.
So the forces themselves aren't truly constant. Their strength depends on how deep you look into this quantum soup.
That's the picture, yes. And it gets even more interconnected. These fluctuations aren't isolated to one field. Quantum fluctuations in, say, the electromagnetic field can cause disturbances in the electron field, the quark field, and so on.
They all talk to each other through the vacuum.
Exactly. It suggests elementary particles are really complex structures, constantly interacting with this dynamic vacuum.
It's complex down there. What about the big picture, the cosmos? You mentioned these fluctuations might have cosmic consequences.
Oh, absolutely. Huge ones. You know the cosmic microwave background, the CMB, the faint afterglow of the Big Bang?
Yeah, the baby picture of the universe.
Well, the tiny temperature variations, the hot spots and cold spots you see in that picture. The prevailing theory is that those originated as quantum fluctuations in a field called the inflaton field, way back in the very first fraction of a second.
Tiny quantum jitters became
Colossally enlarged by the rapid expansion of the universe, cosmic inflation. Those tiny fluctuations were the seeds that gravity later grew into the galaxies and large-scale structures we see today.
So the largest structures in the universe grew from the smallest quantum effects.
It's an incredible connection, a direct, visible imprint of quantum fluctuations on the cosmos.
Wow. Okay, one more thing on this. What about Heisenberg's uncertainty principle? Is that causing all these fluctuations?
Good question. It's actually the other way around. The uncertainty principle is more like a consequence. It's a mathematical statement about the limits of what we can know simultaneously.
So it describes the fuzziness.
It describes the fuzziness that results from the inherent, spontaneous randomness of the vacuum fluctuations. The fluctuations are the underlying physical reality. The uncertainty principle quantifies their effect on measurement.
Right, I see. Well, this quantum vacuum picture is fascinating, but it seems like it also leads to some really big unanswered questions, doesn't it?
It absolutely does. We've uncovered a lot, but we've also hit some major walls.
Like what? What are the biggest puzzles remaining?
Probably the most famous and maybe the most embarrassing for physics is the cosmic vacuum energy discrepancy. also called the cosmological constant problem.
Okay, what's the issue there?
Well, if you take our quantum field theories seriously, and you try to calculate the total energy density packed into the vacuum due to all these fluctuations,
Uh-oh, I sense a problem coming.
you get an absolutely enormous number.
Yeah.
Some calculations even suggest it's technically infinite, though physicists have ways to handle that. But even using reasonable cutoffs, the predicted energy density is huge.
Okay, but what do we actually observe?
When astronomers measure the energy density of space, by looking at how the expansion of the universe is accelerating, attributing that acceleration to dark energy, which behaves like vacuum energy,
Yes.
the value they measure is tiny, incredibly ridiculously small, something like 6 times 10 joules per cubic meter.
So theory predicts enormous. Observation shows tiny.
Worse than tiny. The discrepancy is something like 120 orders of magnitude. That's a 1 followed by 120 zeros. It's arguably the worst prediction in the history of
There's
physics.
120 orders of magnitude. That's staggering. We basically have no idea why they disagree so wildly.
Honestly, no, we don't. There are ideas, potential cancellations, maybe new physics like supersymmetry could help, but right now, it's a massive mystery.
Okay, that's a big one. Any other major enigmas related to this vacuum activity?
Well, there's something a bit more subtle but still profound. We talked about the intense activities, the infinite randomness of these quantum fields, right?
Yeah, the constant jittering and fluctuations.
Yet despite all that chaos, the average values of these fields, the things we measure like the electron's charge or its G factor, they are incredibly stable and precise. Remember, 1 part in a trillion accuracy for the G factor.
Right, so how can it be so chaotic yet so stable on average?
That's the puzzle. What mechanism allows for all these ceaseless, unpredictable fluctuations without contributing a net measurable energy effect, apart from that tiny cosmological constant? And how do the fundamental properties defined by these fields remain so constant, so immutable amidst all the underlying turmoil?
It's like a stormy sea with a perfectly calm surface average.
That's a decent analogy. It's another deep question about the fundamental nature of these fields.
This really seems to circle back to a core tension, doesn't it? The kind we touched on with the APM. It's this pull between wanting, mechanical, visualizable explanations
Like the APM tries to provide.
versus the sheer power and predictive accuracy of the abstract mathematical descriptions that mainstream physics uses, like quantum field theory.
It really is a fundamental debate, almost philosophical, within physics. What constitutes true understanding? Is it a picture you can visualize? Or is it a mathematical framework that makes predictions matching reality to incredible precision?
And things like Bell's theorem experiments, they seem to push against purely local mechanical pictures, right? By showing quantum mechanics has this apparent non-locality.
Exactly. Bell's work ruled out a large class of local hidden variable theories that try to explain quantum weirdness with underlying classical mechanisms hidden from us. It forces us to confront either non-locality or give up some other classical intuition.
So critics of the more mechanical ether-like models might point to that. Plus, as you said, the lack of mathematical rigor compared to established theories, or maybe claims that aren't easily falsifiable.
Those are common criticisms, yes. Along with pointing out that existing theories, like quantum electrodynamics, already explain things like electron behavior or light phenomena incredibly well without needing an underlying physical medium like an ether. They work within the framework of fields and relativity.
So the argument from the mainstream perspective is often that our everyday intuition, our desire to visualize things mechanically, just might not apply at the quantum level.
That's a very common viewpoint. That math is the appropriate language, the unambiguous logic needed to describe how the universe behaves at its most fundamental level, even if it defies easy visualization. And the success, the accuracy to 10+ decimal places, is hard to argue with.
It's a fascinating tension. So what a journey we've taken today. We've really dived into the unseen universe, haven't we?
We definitely have. From looking at that controversial idea of bringing back the ether, but as a dynamic quantized thing,
to exploring the standard model's view of the quantum vacuum, this sea of fluctuations that's undeniably real, proven by experiments like Casimir and Lambshift.
we've seen how both old ideas revisited and cutting-edge theories are wrestling with these huge questions about reality, unification, the nature of space, time, energy.
It really feels like the edges of physics are still wide open.
They absolutely are. Whether progress comes from rethinking old concepts in new ways, like APM attempts, or from pushing experimental limits to probe the quantum vacuum even deeper, the quest for that complete picture is very much ongoing.
So thinking about all this, what does it really mean that empty space isn't empty? That it's this stormy sea of quantum activity that can apparently seed entire galaxies and fundamentally affect particles?
It challenges our basic intuitions about reality.
And if we think about someone like physicist John Wheeler, who famously said, matter tells spacetime how to curve and spacetime tells matter how to move, well, how does this active, fluctuating quantum vacuum fit into that? Does it change how we think about that relationship between geometry and matter?
That's a profound question right there. Does the vacuum mediate that interaction in a deeper way that we currently understand?
Maybe. It leaves you wondering, what other hidden connections, what other secrets might still be waiting for us to find in this invisible, energetic ocean that's all around us? What might you, listening now, uncover as you think about it?